Let's see how we can use a sign diagram to evaluate a more complex inequality. A sign diagram tells us when a function is either positive or negative. That is, whether the value of the function at a particular point lies above or below the horizontal axis. In this case, we want to rearrange our inequality so we have an equivalent expression of the form fp is greater than 0. When our new function fp on the left-hand side is strictly positive, then our original inequality will hold. We'll start by rearranging our inequality to get 0 on the right-hand side. We subtract 3 and add p to both sides. In a sign diagram, we want our terms to be either multiplied together or dividing one to the other. Our next step then is to get our two terms over a common denominator. P minus 1 over P minus 1 is just 1, of course. We'll multiply that by P minus 3 is greater than 0. We have 2P minus 3 plus P minus 1 times P minus 3 in the numerator. We expand that second term in the numerator. We can simplify the numerator by collecting our like terms, these p's, and cancelling out the 3's. We're left with p squared minus 2p on p minus 1 is greater than 0. It's not quite in the form we need it. So now we have our inequality in a form where we can draw a sign diagram. But remember, this new inequality is equivalent to our old one. So that when this inequality holds, so will this one. We're drawing a sign diagram for the inequality p times p minus 2 on p minus 1 is greater than 0. We'll look at each of those three terms in turn and then combine them to see what the overall sign is for each section. Looking at p first, it's 0 when p is 0. When p is greater than 0, it's positive. When it's less than 0, it's negative, of course. We draw straight lines for positive and dashed lines for negative sections. Next, p minus 2. Well, that will equal 0 when p equals 2. There. When p is greater than 2, it'll be positive. When p is less than 2, it'll be negative. Our third term is p minus 1. That will equal 0 when p equals 1. It will be positive when p is greater than 1 and negative when p is less than 1. So now we have the signs of our three terms. Let's combine them. Our first section is where p is less than 0. So we have a negative, a negative, and a negative. So we have a negative multiplied by a negative. That'll give us a positive divided by a negative. It takes us back to being a negative. From 0 to 1, we have a positive, a negative, and a negative. So that's a positive times a negative, which gives us a negative, divided by a negative, will give us a positive. From 1 to 2, we have a positive multiplied by a negative, gives us a negative, divided by a positive, as though it will give us a negative. And from when p is greater than 2, we have a positive multiplied by a positive divided by a positive, which of course gives us a positive. We have our signs, but that we're not finished yet. We need to consider where our individual terms are equal to 0 and what happens to our function then. So when p is equal to 0, well, our function, will it be equal to 0? When p is equal to 2, again, our function will equal 0, because our numerator is equal to 0. However, when p is equal to 1, our function is undefined. We can't divide by 0. What we can do then is indicate what happens as we approach 1 from below and as we approach 1 from above. So as we approach 1 from below, our function is positive. As we approach 1 from above, our function is negative. So those arrows almost meeting at point 1 show that our overall function is undetermined at point 1. So going back to our original problem, we've got our inequality up here. When is it strictly greater than 0? These are our values of p here. So our function on the left-hand side is strictly positive for the open interval 0 to 1 and the open interval from 2 to plus infinity. So p times p minus 2 on p minus 1 is greater than 0 for values of p between 0 and 1. So for p greater than 0 but less than 1, note the strict inequalities there. Or for p strictly greater than 2. Going back to our original inequality, because these two inequalities are equivalent, then we can say that our original inequality holds for the same values of p.